How many of you are exploring agentic AI applications today or have already deployed agentic AI applications? Okay, I see a few hands, but glad that you're here. We're going to help you with some tools to get started with agentic AI and scale them. Let's take a look at a sample agentic AI application. Consider the company called Cloudfix. They sell apparel and they have a shopping assistant on their website. When a user query comes in, the application might have to look up some context about the user or shipping policies from the organization and then feed it to the model. The model itself might process the user query and then determine that it needs additional information from tools like product information lookup, inventory, or shipping policies. Then the whole information is fed back into a model to summarize and generate an answer for the user. In this flow, the end-to-end latency is something of the order of a few seconds, which causes a bad experience to users. And foundational models, as good as they are to generalizing beyond a single use case, they are compute heavy and tend to accumulate cost and latency. And in this agentic AI flow, we also see that having sequential calls to tools and models also tends to stack up your latency. Is there any way that we can optimize this? Let's look at some queries that Cloudpeak application might receive in practice. They're selling a flagship jacket that is very cool, and users want to understand what are its properties, right? So you might have 3 different users asking these questions, which are phrased differently, but all refer to the same thing. Users are interested in how the jacket holds up in water. And ideally, all these queries should receive the same answer, but they do end up hitting the model and the underlying tool calls. So is there a way that we can optimize this? In traditional caching, whenever we see that a tool or a database is being hit multiple times repeatedly for the same information, we can simply place a cache in front of it and serve the answer from the cache in the order of microseconds, saving cost and latency. We simply take the hash of the query and then index the response that we want against that. But in agentic AI applications, users might ask a wide range of queries that are completely unstructured, phrased differently, and can be a wide range. So how do we match these user queries to retrieve the response? This is where vectors can help. Vectors are a series of numbers that capture the meaning and the intent of your text and place similar meaning text together, closer together in a higher dimensional space. So in our example, all these queries about the Cloudpeak jacket and how it holds up in water are closer together than say like how to pair the jacket with jeans, fashion advice, or shipping policies of the company. So when new queries come in, you can compare the distance between the existing vectors in the cache and then determine how similar the query is to the existing query in the cache. Using this approach, instead of using the exact hash of the query, we can use the vector representation to index the response and then retrieve the response. All of this is well and good, but why should you use Valkey? Many people here are aware of the Valkey search project. Okay, I see a few hands, and when talking to a few of you, I did realize that this might be new to some of you. So Valkey search introduces native vector search capabilities on Valkey, and there are a couple of different capabilities that make it well suited for semantic caching. The first is Valkey provides synchronous write path indexing. So any query that comes in, it automatically gets indexed and ready to be searched so that subsequent queries can retrieve the response without a drop in cache hit rate. Valkey supports replica-aware routing, so you have high availability on your applications, as well as you can scale your read throughput with replicas. Valkey supports multi-threading. I think you've heard this multiple times today. So you can scale your application read and write throughput by moving to higher sized instances. And finally, Valkey Search also has a cross-shared scatter gather that supports adding instances, so you can scale up your cache size without application changes. As a result of all this, you can store, search, and update billions of vectors within Valkey with latency as low as microseconds. Let's take a look at how a sample application of semantic cache would look like with Valkey and LangGraph. Cloudpeak would simply store the user query along with the vector embeddings and the answer that must be returned, along with other metadata like product IDs or any ongoing sales and promotions. LangGraph provides a simplified method for you to define a semantic cache. You can simply define a Valkey store with the embedding model that you want to use and the fields that you want to vectorize. In our case, we simply want to take the query from the user and then create vector embeddings for that. You can query your semantic cache by simply passing the user message and retrieve results that contain similarity of how your current query compares to your prior query. Let's take a look at how the architecture would look like in practice. You have LangGraph and the LLM model, with LangGraph handling the orchestration of the agent flow, calling of the tools and the model. We add an embedding model and the Valkey cache. And whenever a user query comes in, we create the vector embeddings for it and check the cache for any prior queries that are similar. If we find that there are prior queries, we look at their similarity to the current query. And if it passes a certain threshold, that is, if it's similar enough, we can simply return the response from the cache. Otherwise, we are going to go hit the model and then any subsequent tool calls, then return the generated response to the user, and then store the response in the cache for subsequent queries. Earlier, we saw that generating a response from the model took about a few seconds, but returning it from the cache directly would be in the order of a few milliseconds. That's a drastic change in latency over generating a new response every single time. Looking at the costs, generating an answer from the model would be about $9. This depends obviously on the model and the number of tokens, but considering Amazon Titan, this is where we stand. But returning an answer from the cache would be about an order of magnitude lower at 20 cents. It depends on the cache that you choose. Here we're using a R7G XL with two replicas. As a consequence of this difference in the price between the model and the cache, we are able to decrease the cost the more responses that you serve from the cache. So here in the graph, you see the cache trace, which captures how many responses you serve from the cache, and the cost goes down in proportion to how many responses you can serve from the cache. This is good, but let's see this application in practice. Let's say Cloudpeak has now a sale. It's Black Friday, and users are lining up to buy their jacket before it goes out of stock. We are going to run a simulation of users coming onto the website and maybe having 1,000 queries in 3 minutes on this application. Here we start out the cache empty. There are no queries in the cache. And then we're going to start the simulation. We are going to measure the cache hit rate, the latency of serving from the cache, which is the second number here. We're going to see how much cost reduction that we have and the total number of requests that we're processing. Initially, since we started out the cache empty and there's not a lot of queries, we're going to see a lot of fluctuation in cache hit rate and low cache hit rates. But as time progresses and the simulation runs, we see the cache, most of the responses gets out from the cache. In this scenario, we see about 70% of the responses being served from the cache. And although there's a peak of users coming in because of Black Friday, we're able to serve with an average latency of about 800 milliseconds. And we are able to achieve 67% cost savings. Okay. Let's look at some best practices for semantic caching. Whenever we have an agentic AI application, we might have a series of prompt instructions and metadata like current time that we pass in to the application along with the user prompt to ensure that you have like a high enough vector match rate. It's suggested that you strip these fields and then use only the user query to index your response. Coming to multi-turn applications, the prior text and conversation from the user might be very relevant to generating an appropriate response for the user's query. But there might be a lot of information that might not be relevant or helpful and will reduce the similarity match in vectors. So instead, we should summarize all the prior context and use that along with the current query to cache. In terms of ensuring your response accuracy, there's a similarity threshold between the vectors that's returned every single time we fetch from the query, from the cache. We can apply a threshold on it, and applying a high enough threshold ensures that your queries are sufficiently similar before you reuse the results. Additionally, we can also apply other filters on tag and numeric fields. Going back to our CloudPeak example, we can use filters on product ID. So before we match the vectors, we can filter for just the CloudPeak jacket, or we can also filter for country, codes, and sales. The final problem is the age-old problem of cold start. If your cache is empty, that like we have seen in our demo, most of the responses are going to be hitting the model instead of coming from the cache, and this increases your cost. To add frequently asked questions and context that we expect from the user, and then pre-populate the cache with this. We do have the demo as a code sample here. If you're interested, please take a photo or scan this to get started. I do want to call out that Valkey integrates with a range of popular agentic AI frameworks. So if you have an agentic AI stack of your preference, you can use Valkey with that. You can also use Valkey for other use cases like agentic memory or real-time semantic search, in addition to semantic caching. Okay. Before I close out, I want to thank the search team for the contributions to the project. And there's a lot more upcoming new features in the space, like text search. We have RFC24. Please go and check it out. We would love for you to get involved with the project. And finally, if you have any questions, you can catch me outside during the break or during the happy hour. Thank you.